Picture this: two galaxies, each containing billions of stars, hurtling toward each other at unimaginable speeds. When they collide, it's not chaos, it's creation. These cosmic collisions are the universe's way of building, destroying, and reshaping itself on a scale so vast it's almost impossible to comprehend. From the birth of galaxies to the extinction of dinosaurs, these monumental events have left their mark on everything we see, and even on us. In this video, we're diving into 25 of the most massive cosmic collisions that have shaped the universe as we know it. These aren't just random accidents, they're the turning points that have defined the cosmos from the very beginning to the present day. Each collision holds secrets about how the universe works, how life began, and what the future might hold. So, buckle up. We're about to take a journey through time and space, exploring the explosive, awe-inspiring moments that have made the universe what it is today. By the end of this video, you'll see the cosmos in a whole new light, and you might just realize how small, yet how connected we truly are. Let's begin. Now turning to the very beginning of everything, we arrive at the ultimate cosmic collision, the Big Bang. This wasn't just an explosion, it was the birth of the universe itself. Imagine a single point, unimaginably dense and hot, suddenly expanding faster than the speed of light. In that moment, space, time, and matter were born. The universe as we know it began to take shape, and the stage was set for everything that would follow. The Big Bang wasn't just a one-time event, it was the foundation of all cosmic history. Within the first fractions of a second, the universe underwent rapid expansion, a process known as inflation. This expansion smoothed out the early universe, creating the conditions for the first particles to form. Protons, neutrons, and electrons began to emerge, eventually combining to create the simplest elements, hydrogen and helium. But the Big Bang didn't just create matter, it also set the rules for how the universe would evolve. The laws of physics, the forces that govern everything from atoms to galaxies, were established in those first moments. Without the Big Bang, there would be no stars, no planets, no galaxies, and certainly no us. This monumental event is the cornerstone of modern cosmology. Scientists have pieced together evidence for the Big Bang through observations like the cosmic microwave background radiation, a faint glow that fills the universe and serves as a snapshot of its infancy. It's a reminder that every star, every planet, and every living thing owes its existence to this colossal collision. The Big Bang wasn't just the beginning, it was the spark that ignited the story of the universe. And as we'll see, every cosmic collision that followed has been a chapter in that ongoing saga. Now turning to the next chapter in the story of the universe, we explore the formation of our very own cosmic home, the Milky Way. This majestic spiral galaxy, with its billions of stars and swirling arms, didn't always look the way it does today. Its story is one of growth, shaped by a series of dramatic collisions and mergers with smaller galaxies over billions of years. The process that built the Milky Way is often called galactic cannibalism. Imagine a cosmic dance where larger galaxies consume smaller ones, absorbing their stars, gas, and dark matter. These collisions weren't violent crashes but slow, gravitational interactions that stretched and pulled the smaller galaxies apart, eventually merging them into the Milky Way. Each merger added to the galaxy's mass and complexity, shaping its structure and size. But the Milky Way's evolution wasn't just about stars and gas. Dark matter, the invisible substance that makes up most of the universe's mass, played a crucial role. It acted like a cosmic scaffold, guiding the formation of the galaxy and holding it together. Without dark matter, the Milky Way as we know it wouldn't exist. Even today, the Milky Way continues to grow and change. It's currently in the process of absorbing smaller satellite galaxies like the Sagittarius dwarf galaxy. These ongoing collisions trigger bursts of star formation and reshape the galaxy's structure, ensuring that the Milky Way is never static but always evolving. The story of the Milky Way is a testament to the power of cosmic collisions. Each merger, each interaction has left its mark, creating the galaxy we call home. And as we'll see, these galactic encounters are far from over. The Milky Way's next great collision is already on the horizon, setting the stage for an even more dramatic chapter in its history. Now turning to the next cosmic event that will reshape our universe, we look ahead to a collision that's already written in the stars, the future merger of the Milky Way and the Andromeda Galaxy. This monumental event, predicted to occur in about 4.5 billion years, will be one of the most dramatic encounters in the history of our galaxy. The science behind this prediction is rooted in the relentless pull of gravity. Both the Milky Way and Andromeda are moving toward each other at a speed of roughly 110 kilometers per second. This motion is driven by their mutual gravitational attraction, a force so powerful that it will eventually bring these two giants together. Despite the vast distances between them, the inevitability of this collision is a reminder of how gravity shapes the cosmos on the grandest scales. So, what will this collision look like? Unlike the explosive crashes we might imagine, this merger will be a slow, graceful dance spanning billions of years. As the galaxies approach, their gravitational forces will stretch and distort their shapes, pulling out long streams of stars and gas. The stars themselves are unlikely to collide, given the immense distances between them, but the gas and dust within the galaxies will interact, triggering bursts of new star formation. Over time, the Milky Way and Andromeda will merge into a single, larger galaxy, often referred to as Milkomeda or Milkdromeda. This new galaxy will likely take on an elliptical shape, a stark contrast to the spiral structures of its predecessors. The supermassive black holes at the centers of both galaxies will also merge, releasing tremendous amounts of energy in the process. This collision will mark the end of the Milky Way as we know it, but it will also give birth to something entirely new. The stars from both galaxies will mingle, creating a cosmic tapestry that tells the story of their shared history. And while this event is far in the future, it serves as a powerful reminder of the dynamic, ever-changing nature of the universe. As we continue our journey through the cosmos, we'll explore more collisions that have shaped the universe, each one a testament to the incredible forces at work in the vast expanse of space. Now turning to a collision that shaped not just the cosmos, but our very own planet, we delve into the moon-forming impact. This monumental event, often referred to as the giant impact hypothesis, suggests that around 4.5 billion years ago, a Mars-sized body, sometimes called Theia, collided with the early Earth. The force of this collision was so immense that it ejected a massive amount of debris into orbit around our planet. Over time, this debris coalesced to form the Moon, Earth's closest celestial companion. The evidence supporting this theory is compelling. Scientists have found striking similarities in the isotopic compositions of Earth and Moon rocks, particularly in elements like oxygen. These similarities suggest that both bodies share a common origin, pointing to a shared history forged in the aftermath of this colossal impact. Additionally, computer simulations of the collision align with the current orbital and rotational dynamics of the Earth-Moon system, further bolstering the hypothesis. But the moon-forming impact did more than just create our lunar neighbor. It also played a crucial role in shaping Earth's rotation and axial tilt. The collision imparted a significant amount of angular momentum to Earth, setting the stage for the length of our days and the stability of our seasons. Without this event, Earth's rotation might have been much faster, leading to shorter days and a vastly different climate. The axial tilt, which gives us our seasons, was also influenced by this impact, creating the conditions necessary for the diverse and stable climate we enjoy today. This collision was a defining moment in Earth's history, not only giving us the Moon but also setting the stage for the planet's habitability. The Moon's gravitational pull stabilizes Earth's axial tilt, preventing extreme climate fluctuations that could have made life as we know it impossible. It also drives the tides, which have played a crucial role in the evolution of life on our planet. As we reflect on this cosmic event, we're reminded of how interconnected the universe truly is. A single collision billions of years ago set in motion a chain of events that shaped the Earth and made it a haven for life. And as we continue our exploration of the cosmos, we'll uncover more collisions that have left their mark on the universe, each one a testament to the incredible forces that shape the world around us. Now turning to a period of cosmic chaos that reshaped the early solar system, we explore the Late Heavy Bombardment. This intense era, occurring around 4 billion years ago, was marked by a relentless barrage of asteroids and comets colliding with the inner planets, including Earth. Imagine a time when the skies were filled with fiery projectiles, each impact leaving behind scars that would shape the future of our planet and its neighbors. The Late Heavy Bombardment was a critical phase in the solar system's history. During this time, the inner planets, still in their formative stages, were bombarded by countless asteroids and comets. These collisions were so frequent and powerful that they completely reshaped the surfaces of planets like Mercury, Venus, Mars, and Earth. Craters formed by these impacts can still be seen today, serving as a reminder of this tumultuous period. But the Late Heavy Bombardment wasn't just about destruction. It also played a vital role in delivering the building blocks of life to Earth. Many scientists believe that the comets and asteroids that struck our planet during this time carried water and organic molecules. These essential ingredients deposited on Earth's surface may have set the stage for the emergence of life. The water from these impacts could have filled Earth's early oceans, while the organic molecules provided the raw materials necessary for the first living organisms. This period of intense collisions also had a profound impact on the geological and atmospheric evolution of Earth. The constant bombardment heated the planet's surface, triggering volcanic activity and releasing gases that contributed to the formation of the early atmosphere. Over time, these processes helped create the conditions necessary for life to thrive. As we reflect on the Late Heavy Bombardment, we see how this chaotic period was a crucial step in the journey toward a habitable Earth. The collisions that once seemed like pure devastation ultimately laid the groundwork for the rich and diverse planet we call home. And as we continue to explore the cosmos, we'll uncover more about how these ancient events shaped not just Earth, but the entire solar system. Now turning to one of the most dramatic and transformative events in Earth's history, we explore the Chicxulub Impact. This colossal asteroid collision, occurring 66 million years ago, marked the end of the age of dinosaurs and set the stage for the rise of mammals, including our own ancestors. The impact, centered in what is now the Yucatan Peninsula in Mexico, unleashed unimaginable destruction, reshaping life on Earth in ways that still echo today. The Chicxulub asteroid, estimated to be about 6 miles in diameter, struck Earth with the force of billions of atomic bombs. The immediate effects were catastrophic. The impact generated a massive shockwave that flattened everything within hundreds of miles, while the heat from the collision ignited global wildfires. Dust and debris were hurled into the atmosphere, blocking sunlight and plunging the planet into a prolonged period of darkness and cold. This impact winter disrupted photosynthesis, causing the collapse of plant life and, in turn, the ecosystems that depended on it. But the devastation didn't end there. The long-term effects of the Chicxulub impact were equally profound. The release of sulfur compounds and carbon dioxide into the atmosphere triggered drastic climate changes, including acid rain and global warming. These environmental shifts made it nearly impossible for many species to survive, leading to the extinction of around 75% of all life on Earth, including the non-avian dinosaurs. Yet, from this devastation emerged new opportunities. The extinction of the dominant dinosaurs allowed smaller, more adaptable mammals to thrive. Over millions of years, these mammals diversified and evolved, eventually giving rise to the incredible variety of life we see today, including humans. The Chicxulub Impact, while a tragedy for the dinosaurs, was a turning point that paved the way for the rise of mammals and the eventual emergence of intelligent life. As we reflect on this monumental event, we see how a single collision could alter the course of life on Earth. The Chicxulub Impact reminds us of the delicate balance that sustains life and the profound ways in which cosmic events can shape our planet's history. And as we continue to explore the universe, we'll uncover more about how these collisions have influenced not just Earth, but the broader story of life itself. Now turning to another extraordinary cosmic event, we delve into the Tunguska Event, a mysterious explosion that shook the remote forests of Siberia in 1908. This event, often described as one of the most powerful explosions in recorded history, remains a fascinating puzzle for scientists and a stark reminder of the potential dangers lurking in our skies. On the morning of June 30, 1908, a massive fireball streaked across the sky over the Tunguska region. Moments later, an explosion equivalent to 10 to 15 megatons of TNT flattened an estimated 80 million trees across 800 square miles. The shockwave was so powerful that it knocked people off their feet hundreds of miles away and was detected as far as Europe and Asia. Yet, despite the immense destruction, no crater was found at the site, leaving scientists baffled for decades. The leading theory suggests that the explosion was caused by a meteoroid or comet fragment entering Earth's atmosphere. As it descended, the intense heat and pressure caused it to disintegrate and explode several miles above the ground, releasing an enormous amount of energy without leaving a crater. This phenomenon, known as an airburst, explains the widespread devastation and the absence of a traditional impact site. The Tunguska event has profound implications for our understanding of near-Earth objects and the potential threats they pose. It serves as a stark reminder that even relatively small cosmic bodies can cause catastrophic damage if they collide with Earth. Today, scientists closely monitor near-Earth objects to assess potential risks and develop strategies to mitigate the impact of future collisions. As we reflect on the Tunguska event, we're reminded of the delicate balance between our planet and the vast cosmos. This mysterious explosion not only reshaped a remote corner of Siberia, but also reshaped our understanding of the universe's potential to influence life on Earth. And as we continue to explore the skies, events like Tunguska remind us of the importance of vigilance and preparedness in the face of cosmic uncertainty. Now turning to another monumental cosmic event, we explore the Shoemaker-Levy 9 impact on Jupiter, a collision that captivated astronomers and reshaped our understanding of planetary impacts. In July 1994, the world witnessed an extraordinary event as fragments of comet Shoemaker-Levy 9 collided with Jupiter, marking the first time scientists directly observed a cosmic collision in our solar system. Discovered in March 1993 by Carolyn and Eugene Shoemaker and David Levy, the comet had already been torn apart by Jupiter's immense gravitational forces during a previous close encounter. This left it as a chain of 21 fragments, each destined to collide with the gas giant. Over the course of 6 days, these fragments slammed into Jupiter's atmosphere at speeds of over 130,000 miles per hour, releasing energy equivalent to millions of nuclear bombs. The impacts created massive fireballs and left dark scars in Jupiter's atmosphere, some larger than Earth itself. These scars were visible for months, providing scientists with an unprecedented opportunity to study the aftermath of such collisions. The event revealed critical insights into the dynamics of planetary impacts, including how shockwaves propagate through a planet's atmosphere and how debris from the collision interacts with its environment. One of the most significant lessons from the Shoemaker-Levy 9 impact was the realization of how common such collisions might be in the solar system. Jupiter, with its strong gravitational pull, often acts as a cosmic shield, drawing in comets and asteroids that might otherwise threaten Earth. This event underscored the importance of monitoring near-Earth objects and understanding the potential risks they pose to our planet. The Shoemaker-Levy Impact not only deepened our knowledge of planetary science, but also highlighted the dynamic and ever-changing nature of our solar system. As we continue to explore the cosmos, events like this remind us of the powerful forces at play and the need to remain vigilant in our quest to understand the universe. Now turning to the very foundation of our cosmic neighborhood, we delve into the formation of the solar system, a story of chaos, collisions, and creation. Around 4.6 billion years ago, a vast cloud of gas and dust known as the solar nebula began to collapse under its own gravity. This collapse set the stage for a series of dramatic events that would eventually give birth to the Sun, the planets, and all the celestial bodies we know today. As the solar nebula contracted, it began to spin faster, flattening into a rotating disk. At the center, the material grew denser and hotter, eventually igniting nuclear fusion and forming the Sun. Meanwhile, in the outer regions of the disk, tiny particles of dust and ice started to stick together, forming larger clumps called planetesimals. These planetesimals, ranging from a few meters to several kilometers in size, became the building blocks of the planets. Over millions of years, these planetesimals collided and merged through a process called accretion. Each collision added mass, gradually forming protoplanets. Some of these protoplanets grew large enough to dominate their orbits, clearing out smaller debris and becoming the planets we recognize today. Others, like those in the asteroid belt, remained as remnants of this chaotic era. The inner solar system, closer to the Sun, was dominated by rocky planets like Earth and Mars, as the intense heat vaporized lighter materials, leaving behind metals and silicates. In contrast, the outer solar system, where temperatures were much colder, allowed for the accumulation of gases and ices, leading to the formation of gas giants like Jupiter and Saturn, as well as icy bodies like Uranus and Neptune. This process wasn't without its violent moments. Massive collisions between protoplanets shaped the final structure of the solar system. For instance, the collision between Earth and a Mars-sized body, often referred to as Theia, is believed to have led to the formation of the Moon. Similarly, the gravitational tug-of-war between Jupiter and other protoplanets likely scattered debris, influencing the distribution of asteroids and comets. The formation of the solar system was a complex dance of gravity, collisions, and accretion, leaving behind a diverse array of worlds. From the rocky inner planets to the gas giants and icy bodies of the outer reaches, each celestial body carries the scars and stories of these ancient cosmic collisions. As we continue to explore our solar system, we uncover more clues about its turbulent beginnings, reminding us of the dynamic and ever-evolving nature of the universe. Now turning to one of the most pivotal moments in Earth's history, we revisit the KT boundary impact, a collision that forever altered the course of life on our planet. Around 66 million years ago, a massive asteroid, estimated to be about 6 miles in diameter, struck Earth near what is now the Yucatan Peninsula in Mexico. This catastrophic event marked the end of the Cretaceous period and the beginning of the Paleogene, leaving behind a geological boundary known as the KT boundary. The impact unleashed unimaginable destruction. The energy released was equivalent to billions of atomic bombs, triggering massive wildfires, tsunamis, and a global shockwave. Dust and debris were hurled into the atmosphere, blocking sunlight for months or even years. This led to a dramatic drop in temperatures, disrupting photosynthesis and collapsing food chains. The result was a mass extinction event that wiped out approximately 75% of Earth's species, including the non-avian dinosaurs, which had dominated the planet for over 150 million years. Evidence of this cataclysmic event is preserved in the geological record. One of the most striking pieces of evidence is the iridium layer, a thin band of sediment found worldwide. Iridium is a rare element on Earth but is abundant in asteroids. The discovery of this layer in the late 1970s provided strong support for the asteroid impact theory. Additionally, shocked quartz and tektites, glassy beads formed from molten rock, have been found in the same layer, further confirming the violent nature of the collision. The KT boundary impact not only reshaped life on Earth but also paved the way for the rise of mammals, including our own ancestors. Without this collision, the evolutionary path of life might have been entirely different. As we study this event, we gain a deeper understanding of the fragility and resilience of life, as well as the profound impact that cosmic collisions can have on the history of our planet. Now turning to the majestic beauty of our solar system, we explore the formation of Saturn's rings, one of the most iconic features in the cosmos. Scientists believe these stunning rings were born from a dramatic collision, possibly involving a moon or a comet that ventured too close to Saturn. The immense gravitational forces of the gas giant tore the object apart, scattering its debris into space. Over time, this debris was captured by Saturn's gravity, forming the intricate rings we see today. The rings are composed of countless particles, ranging from tiny grains of dust to massive chunks of ice and rock, all orbiting Saturn in a delicate balance. But the story doesn't end there. Saturn's rings are not static. They are constantly shaped and maintained by ongoing processes. The planet's gravity, along with the gravitational influence of its many moons, keeps the particles in motion, creating gaps, waves, and intricate patterns within the rings. Some moons, like tiny shepherds, even help confine the rings and prevent them from spreading out too far. What makes Saturn's rings even more fascinating is their dynamic nature. Collisions between ring particles as well as interactions with micrometeoroids continuously reshape the rings, making them a living, evolving system. This ongoing activity ensures that the rings remain one of the most captivating sights in our solar system, offering us a glimpse into the complex interplay of gravity, collisions, and cosmic debris. As we marvel at Saturn's rings, we are reminded of the incredible forces that shape our universe, turning chaos into beauty and destruction into creation. These rings are not just a stunning visual spectacle, they are a testament to the enduring power of cosmic collisions and the intricate dance of celestial bodies. Now turning to the vast expanse of the universe, we delve into one of the most monumental events in cosmic history, the Great Galactic Collision. This colossal event occurred when two galaxies, each containing billions of stars, planets, and vast clouds of gas and dust, collided and merged over millions of years. The result was the birth of a massive elliptical galaxy, a cosmic giant that stands as a testament to the transformative power of such collisions. Evidence of these galactic mergers can be seen in the remnants they leave behind. Tidal tails, long streams of stars and gas, stretch out into space, marking the paths where galaxies once passed by each other. Star streams, formed from stars ripped away by gravitational forces, also trace the violent history of these encounters. These features serve as cosmic fingerprints, allowing astronomers to piece together the story of these ancient collisions. But the impact of such events goes far beyond their visual remnants. When galaxies collide, the immense gravitational forces compress gas and dust, triggering bursts of star formation. These starbursts light up the merging galaxies, creating some of the brightest and most active regions in the universe. The collision also reshapes the structure of the galaxies involved, often transforming spiral galaxies into elliptical ones with their smooth, featureless appearance. The Great Galactic Collision not only reshapes the galaxies involved but also influences their future evolution. The merger can lead to the formation of supermassive black holes at the center of the new galaxy, which in turn can power quasars and other energetic phenomena. These collisions are a reminder of the dynamic and ever-changing nature of the universe, where destruction and creation are intertwined in a cosmic dance. As we reflect on the Great Galactic Collision, we gain a deeper appreciation for the forces that shape the cosmos. These events, though violent and chaotic, are essential to the evolution of galaxies, driving the formation of new stars and reshaping the structure of the universe itself. They remind us that even in the vastness of space, change is constant, and beauty can emerge from the most dramatic of events. Now turning to the outer reaches of our solar system, we explore the mysterious and distant Oort cloud, a vast shell of icy objects that encircles the Sun far beyond the orbit of Neptune. This enigmatic region, named after the Dutch astronomer Jan Oort, is believed to have formed from the gravitational scattering of debris during the chaotic early days of the solar system. As planets and other bodies collided and interacted, some of the leftover material was flung outward by the gravitational forces of the giant planets, settling into a distant spherical cloud that marks the boundary of the Sun's influence. The Oort cloud is thought to be the source of long-period comets, those icy visitors that occasionally streak through the inner solar system on orbits that can take thousands or even millions of years to complete. When a passing star or the gravitational pull of the Milky Way disturbs the Oort cloud, some of these icy bodies are nudged inward, beginning their long journey toward the Sun. As they approach, the heat causes their ices to vaporize, creating the spectacular tails that make comets so mesmerizing to observe. Understanding the Oort cloud is crucial to unraveling the history of our solar system. It serves as a cosmic time capsule, preserving material from the very beginning of the solar system's formation. By studying the composition of comets that originate from the Oort cloud, scientists can gain insights into the conditions and processes that shaped the early solar system. These icy remnants offer clues about the distribution of elements and the dynamics of planetary formation, helping us piece together the story of how our cosmic neighborhood came to be. The Oort cloud also reminds us of the vastness of the solar system and the delicate balance of forces that govern it. While it may seem like a remote and unchanging region, it plays a vital role in the ongoing evolution of our cosmic environment. As we continue to explore and study this distant frontier, we uncover not only the secrets of our past but also the potential for future discoveries that could reshape our understanding of the universe. Now turning to the region just beyond Neptune, we encounter the Kuiper Belt, a vast expanse of icy bodies that holds clues to the early history of our solar system. This distant ring of frozen objects, stretching from Neptune's orbit out into the depths of space, was shaped by a series of collisions and gravitational interactions during the solar system's chaotic formation. As the giant planets like Jupiter and Saturn migrated and settled into their current positions, their immense gravity influenced the distribution of material in the outer solar system, pushing smaller bodies outward and sculpting the Kuiper Belt into its present form. The Kuiper Belt is home to a diverse array of objects, from small icy fragments to larger bodies like Pluto, which was reclassified as a dwarf planet in 2006. These icy remnants are thought to be pristine relics from the solar system's infancy, preserving the original building blocks that never coalesced into full-fledged planets. By studying these objects, scientists can gain valuable insights into the conditions and processes that governed the outer solar system billions of years ago. For example, the composition of Kuiper Belt objects reveals information about the distribution of water, methane, and other volatile compounds, which were crucial ingredients in the formation of planets and moons. One of the most fascinating aspects of the Kuiper Belt is its role as the birthplace of short-period comets. Unlike the long-period comets that originate in the distant Oort cloud, short-period comets are thought to come from the Kuiper Belt. When gravitational interactions or collisions disturb the orbits of these icy bodies, they can be nudged inward, embarking on a journey toward the Sun. As they approach, the heat causes their ices to sublimate, creating the glowing comas and tails that make comets so captivating to observe. The discovery of the Kuiper belt has fundamentally changed our understanding of the solar system. It has revealed that the outer reaches are far more dynamic and complex than previously imagined, with a rich tapestry of objects that tell the story of our cosmic origins. By exploring this distant frontier, we not only uncover the history of our own solar system, but also gain insights into the formation of other planetary systems across the galaxy. The Kuiper belt serves as a reminder that even the most remote corners of our cosmic neighborhood hold secrets waiting to be discovered, shaping our understanding of the universe and our place within it. Now turning to the story of Earth's oceans, we delve into one of the most transformative chapters in our planet's history. The vast, life-sustaining waters that cover more than 70% of Earth's surface may owe their existence to a series of cosmic collisions that occurred billions of years ago. During a period known as the Late Heavy Bombardment, Earth was relentlessly pummeled by comets and asteroids, delivering not only destruction but also the essential ingredient for life, water. Scientists believe that these icy comets, originating from the outer reaches of the solar system, carried water in the form of ice. When they collided with Earth, the heat from the impacts vaporized the ice, releasing water vapor into the atmosphere. Over time, as the planet cooled, this vapor condensed and fell as rain, gradually filling the basins that would become Earth's oceans. This theory is supported by the isotopic composition of water found on Earth, which closely matches that of water in comets. Specifically, the ratio of hydrogen to deuterium, a heavier isotope of hydrogen, in Earth's water aligns with the ratios observed in cometary ice, suggesting a shared origin. These collisions did more than just deliver water. They played a crucial role in making Earth a habitable planet. The presence of liquid water allowed for the development of complex chemical reactions, paving the way for the emergence of life. Additionally, the oceans helped regulate Earth's climate by absorbing and redistributing heat, creating stable conditions that supported the evolution of diverse ecosystems. Without these ancient impacts, Earth might have remained a barren, waterless world, devoid of the vibrant life that thrives today. The formation of Earth's oceans is a testament to the profound impact of cosmic collisions on the evolution of planets. These events not only shaped the physical landscape of our world, but also set the stage for the emergence of life, highlighting the intricate interplay between chaos and creation in the cosmos. As we continue to explore the mysteries of our solar system, the story of Earth's oceans reminds us of the delicate balance that makes our planet unique and the extraordinary processes that have shaped its history. Now turning to the Moon's mysterious dark plains, we uncover the story of how its maria were formed. These vast, flat regions, visible even from Earth, are the result of colossal asteroid impacts that occurred billions of years ago. When these massive objects struck the Moon, they created enormous craters, some of which were hundreds of kilometers wide. The energy from these collisions was so immense that it melted the Moon's crust, releasing molten lava that flooded the newly formed basins. Over time, this lava cooled and solidified, creating the smooth, dark plains we see today. Evidence for these ancient impacts can be found in the Moon's geology. The maria are surrounded by impact basins, which are the remnants of the original craters. These basins are often marked by concentric rings of mountains formed by the shock waves of the collisions. Additionally, the age of the maria, determined through radiometric dating of lunar rocks, aligns with the period of intense bombardment that shaped the early solar system. The rocks from the maria are significantly younger than the surrounding highlands, indicating that the lava flows occurred after the Moon's initial formation. These impacts not only shaped the Moon's surface but also influenced its geological history. The maria cover about 16% of the Moon's near side, creating a stark contrast with the brighter, more heavily cratered highlands. This uneven distribution is thought to be due to differences in the thickness of the Moon's crust, with the near side being thinner and more prone to volcanic activity. The formation of the Maria also played a role in the Moon's cooling process, as the lava flows released heat from its interior, helping to stabilize its structure. The story of the Moon's Maria is a powerful reminder of the dynamic forces that have shaped our celestial neighbor. These ancient collisions not only left a lasting mark on the Moon's surface, but also provide valuable insights into the early history of the solar system. As we continue to study the Moon, the Maria stand as a testament to the transformative power of cosmic impacts and the enduring legacy they leave behind. Now turning to the vast expanse between Mars and Jupiter, we explore the story of the asteroid belt, a region shaped by cosmic collisions and gravitational forces. This belt, home to millions of rocky bodies, is a relic of the early solar system, offering clues about its chaotic beginnings. During the formation of the solar system, dust and debris began to clump together, forming planetesimal small, rocky bodies that could have grown into planets. However, in the region between Mars and Jupiter, this process was disrupted by the immense gravitational pull of Jupiter. Jupiter's gravity played a pivotal role in shaping the asteroid belt. As the largest planet in the solar system, its gravitational influence was so strong that it prevented the planetesimals in this region from coalescing into a single planet. Instead, these bodies were scattered and collided with one another, breaking apart rather than merging. Over time, this created a fragmented zone filled with asteroids of varying sizes, from tiny pebbles to massive objects like Ceres, the largest asteroid in the belt. The collisions within the asteroid belt were not just destructive, they were also formative. Each impact chipped away at larger bodies, creating smaller fragments and contributing to the belt's diverse population. These collisions also released dust and debris, which continue to orbit the Sun, adding to the belt's complexity. The asteroid belt is not a dense field of rocks as often depicted in movies. Instead, the asteroids are spread out over a vast area with millions of kilometers between them. Asteroids are more than just remnants of the solar system's formation. They are time capsules that preserve the conditions of the early solar system. By studying their composition, scientists can learn about the materials that existed over 4.5 billion years ago. Some asteroids contain water and organic molecules, suggesting that they may have played a role in delivering these essential ingredients to Earth, potentially influencing the origins of life. The asteroid belt also serves as a reminder of the delicate balance of forces that shaped our solar system. Without Jupiter's gravitational influence, the belt might have formed into another planet, altering the architecture of our cosmic neighborhood. Instead, it remains a dynamic region where collisions continue to shape its inhabitants and provide insights into the processes that built the planets. As we look to the future, the asteroid belt holds both scientific promise and potential challenges. Missions to study asteroids up close, such as NASA's OSIRIS-REx and Japan's Hayabusa 2, are uncovering new details about their composition and history. At the same time, the belt reminds us of the ever-present possibility of asteroids straying from their orbits, posing a risk to Earth. Understanding the asteroid belt is not just about exploring the past, it's about preparing for the future as we continue to unravel the mysteries of our solar system's formation. Now turning to the protective shield that envelops our solar system, we delve into the formation of the Sun's heliosphere. This vast bubble of charged particles, extending far beyond the orbits of the planets, is shaped by the Sun's magnetic field and its interactions with the interstellar medium. The heliosphere acts as a cosmic barrier, shielding the solar system from the high-energy cosmic rays and interstellar dust that permeate the galaxy. The formation of the heliosphere began with the Sun's birth, as its magnetic field began to influence the surrounding space. As the Sun emits a constant stream of charged particles, known as the solar wind, these particles travel outward, colliding with the interstellar material that fills the space between stars. These collisions create a boundary known as the heliopause, where the pressure of the solar wind balances the pressure of the interstellar medium. Beyond this boundary lies the vast expanse of interstellar space. The heliosphere is not static. It is constantly shaped by the Sun's activity and its interactions with the interstellar environment. During periods of high solar activity, the solar wind becomes stronger, pushing the heliopause further out. Conversely, when the Sun is less active, the heliosphere contracts. These fluctuations highlight the dynamic nature of the heliosphere and its role in protecting the solar system. One of the heliosphere's most critical functions is its ability to deflect cosmic rays, high-energy particles that originate from distant supernova and other cosmic events. Without the heliosphere, these particles would bombard the planets, potentially disrupting their atmospheres and posing a threat to life. By acting as a protective bubble, the heliosphere ensures that the solar system remains a relatively safe haven for planets like Earth. Interstellar dust, another component of the interstellar medium, is also filtered by the heliosphere. While some dust particles manage to penetrate the heliopause, many are deflected or slowed down, reducing their impact on the inner solar system. This filtering process helps maintain the delicate balance of materials within the solar system, influencing the formation and evolution of planets and other celestial bodies. The study of the heliosphere is ongoing, with missions like NASA's Voyager probes providing valuable insights into its structure and behavior. Voyager 1 and 2, which have crossed the heliopause and entered interstellar space, continue to send back data about the conditions at the edge of the heliosphere. These missions are helping scientists understand how the heliosphere interacts with the interstellar medium and how it protects the solar system from external threats. As we explore the heliosphere, we gain a deeper appreciation for the Sun's role in shaping our cosmic environment. This protective bubble not only shields the solar system from harmful cosmic rays and interstellar dust, but also serves as a reminder of the interconnectedness of the universe. The heliosphere is a testament to the dynamic processes that govern the cosmos, offering insights into the forces that shape our solar system and the broader galaxy. Now turning to the vast expanse of our galaxy, we explore the formation of the local bubble, a fascinating region of hot, low-density gas that surrounds our solar system. This cosmic structure, spanning hundreds of light years, is believed to have been shaped by a series of supernova explosions and the powerful stellar winds from massive stars. These cataclysmic events, occurring over millions of years, carved out a cavity in the interstellar medium, creating the local bubble as we know it today. The story of the local bubble begins with the death of massive stars. When these stars exhaust their nuclear fuel, they end their lives in spectacular supernova explosions, releasing immense amounts of energy and ejecting material into space. These explosions, along with the stellar winds emitted by young, massive stars, push away the surrounding gas and dust, creating a bubble-like structure. Over time, multiple supernovae in the same region can combine their effects, expanding the bubble further and heating the gas within it to extremely high temperatures. The local bubble is not an isolated phenomenon. It is part of a larger network of similar structures that make up the interstellar medium. These bubbles play a crucial role in shaping the galaxy, influencing the distribution of gas and dust and triggering the formation of new stars and planetary systems. As the shockwaves from supernova and stellar winds compress the surrounding material, they can initiate the collapse of gas clouds, leading to the birth of new stars. This process highlights the interconnectedness of cosmic events, where the death of one generation of stars paves the way for the birth of another. One of the most intriguing aspects of the local bubble is its impact on our own solar system. The bubble's hot, low-density gas surrounds the heliosphere, influencing the environment through which the Sun and its planets travel. This interaction provides scientists with valuable insights into the conditions of the interstellar medium and the forces that shape our cosmic neighborhood. By studying the local bubble, researchers can better understand the history of star formation in our galaxy and the processes that drive the evolution of the Milky Way. The formation of the local bubble also underscores the dynamic nature of the universe. Supernova and stellar winds are not isolated events but part of an ongoing cycle of creation and destruction that shapes the cosmos. These collisions and interactions remind us that the universe is in a constant state of flux, with each event contributing to the intricate tapestry of stars, planets, and galaxies. As we continue to explore the local bubble and its origins, we gain a deeper understanding of the forces that have shaped our galaxy and the broader universe. This region of hot, low-density gas serves as a window into the past, offering clues about the history of star formation and the processes that drive the evolution of the cosmos. The local bubble is a testament to the power of cosmic collisions and their profound impact on the universe we inhabit. Now turning to the earliest moments of the universe, we explore the formation of the cosmic microwave background, a faint glow that permeates the cosmos and serves as a relic of the Big Bang. This radiation, often referred to as the afterglow of the universe's birth, is the oldest light we can observe, dating back to when the universe was just 380,000 years old. It provides a snapshot of the universe in its infancy, offering a glimpse into the conditions that existed shortly after the Big Bang. The cosmic microwave background was formed when the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, allowed photons to travel freely through space for the first time, creating a sea of light that has been stretching and cooling ever since. As the universe expanded, this light shifted to longer wavelengths, eventually becoming the microwave radiation we detect today. The cosmic microwave background is not uniform. It contains tiny fluctuations in temperature, which are the seeds of all the structures we see in the universe today, from galaxies to galaxy clusters. These fluctuations are the result of collisions and interactions in the early universe. In the moments following the Big Bang, the universe was a hot, dense soup of particles and energy. Quantum fluctuations, amplified by the rapid expansion of the universe, created slight variations in density. These variations grew over time as gravity pulled matter together, leading to the formation of the first stars and galaxies. The cosmic microwave background preserves these early density variations, providing a map of the universe's initial conditions. The discovery of the cosmic microwave background in 1965 was a pivotal moment in cosmology. It provided strong evidence for the Big Bang theory, confirming that the universe had a hot, dense beginning. Since then, detailed observations of the cosmic microwave background have allowed scientists to measure the age, composition, and expansion rate of the universe with remarkable precision. These measurements have revealed that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, shaping our understanding of the cosmos. The cosmic microwave background also offers insights into the geometry of the universe. The patterns of temperature fluctuations indicate that the universe is flat, meaning that parallel lines will never meet, and the angles of a triangle add up to 180 degrees. This flatness is a key prediction of the inflationary theory, which suggests that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The cosmic microwave background provides compelling evidence for this theory, helping to explain why the universe appears so uniform on large scales. As we study the cosmic microwave background, we are essentially looking back in time to the universe's earliest moments. This ancient light carries with it the story of how the universe began and how it has evolved over billions of years. It is a testament to the power of cosmic collisions and interactions, which have shaped the universe from its fiery birth to the vast, complex cosmos we see today. The cosmic microwave background is not just a relic of the past, It is a window into the fundamental processes that govern the universe, offering clues about its origins and its ultimate fate. Now turning to the birth of the first stars, we delve into a pivotal moment in cosmic history that forever changed the universe. These first stars, often referred to as population 3 stars, emerged from the collisions and mergers of primordial gas clouds, composed almost entirely of hydrogen and helium. In the early universe, these clouds were the only building blocks available, and their gravitational collapse marked the beginning of stellar formation. As these gas clouds clumped together under the force of gravity, they began to heat up, eventually reaching temperatures high enough to ignite nuclear fusion. This process transformed hydrogen into helium, releasing immense amounts of energy and lighting up the universe for the first time. The formation of these first stars was a monumental event, as they were not only the first sources of light but also the first factories for creating heavier elements. The role of these stars extended far beyond their brilliance. As they burned, they produced elements like carbon, oxygen, and nitrogen through nuclear fusion. When these massive stars exhausted their fuel, they exploded in spectacular supernova, scattering these newly formed elements into the surrounding space. This process, known as nucleosynthesis, seeded the universe with the raw materials needed to form planets, moons, and even life itself. Another critical contribution of the first stars was their role in reionizing the universe. During the cosmic dark ages, the universe was filled with neutral hydrogen, which absorbed light and kept the cosmos shrouded in darkness. The intense ultraviolet radiation from the first stars ionized this hydrogen, stripping electrons from atoms and making the universe transparent to light once again. This era of reionization, which began around 200 million years after the Big Bang, marked the end of the cosmic dark ages and set the stage for the formation of galaxies. The formation of the first stars was a direct result of the density fluctuations preserved in the cosmic microwave background. These fluctuations, which began as tiny ripples in the early universe, grew over time, creating regions of higher density where gas could accumulate and collapse. Without these initial seeds, the first stars might never have formed, and the universe as we know it would not exist. The legacy of the first stars is written across the cosmos. Their light, though long extinguished, paved the way for the galaxies and stars that followed. Their explosions enriched the universe with the elements necessary for life, and their radiation reionized the cosmos, making it possible for light to travel freely. As we look out into the night sky, we are witnessing the enduring impact of these ancient celestial pioneers, whose collisions and creations shaped the universe into the vibrant, dynamic place it is today. Now turning to the formation of supermassive black holes, we explore one of the most mysterious and powerful phenomena in the universe. These colossal structures, found at the hearts of most galaxies, are believed to have formed through a series of dramatic collisions and mergers in the early universe. Imagine a cosmic dance where smaller black holes, born from the deaths of massive stars, came together, merging into ever larger entities. At the same time, vast clouds of gas and dust were drawn into these growing black holes, feeding their insatiable appetites and accelerating their growth. The process began in the chaotic aftermath of the first stars. As these stars exploded in supernova, they left behind black holes, some of which collided and merged under the pull of gravity. Over time, these mergers created black holes of increasing mass, eventually forming the supermassive black holes we observe today. But it wasn't just black holes merging, gas clouds also played a crucial role. As these clouds were pulled into the black holes, they formed swirling disks of material, heating up and emitting intense radiation. This process, known as accretion, not only fueled the growth of the black holes but also released energy that influenced the surrounding galaxy. Supermassive black holes are now understood to be central players in the evolution of galaxies. Their immense gravitational pull shapes the motion of stars and gas, while the energy they release during accretion can trigger star formation or, conversely, halt it by heating up the surrounding gas. This delicate balance between creation and destruction is one of the key ways supermassive black holes influence their host galaxies. Evidence for these cosmic giants comes from observations of their effects on nearby stars and gas, as well as the detection of gravitational waves, ripples in spacetime produced by black hole mergers. The Event Horizon Telescope's groundbreaking image of the black hole at the center of the galaxy Messier 87 further confirmed their existence, providing a glimpse into the shadowy heart of one of these enigmatic objects. The formation of supermassive black holes is a testament to the universe's capacity for both destruction and creation. Through collisions and mergers, these titans emerged, shaping the galaxies around them and leaving an indelible mark on the cosmos. As we continue to study them, we uncover more about the intricate processes that govern the universe, revealing the profound connections between the smallest particles and the largest structures in existence. Now turning to the formation of galaxy clusters, we delve into the creation of the largest structures in the universe. These immense gatherings of galaxies, bound together by gravity, are the result of countless collisions and mergers over billions of years. Picture a cosmic tapestry where smaller galaxies, each with their own stars, gas, and dark matter, are drawn together by the invisible threads of gravity, eventually forming these colossal clusters. At the heart of this process lies dark matter, the mysterious substance that makes up most of the universe's mass. Though invisible, dark matter's gravitational pull is the driving force behind the formation of galaxy clusters. As galaxies move through space, they are guided by the gravitational influence of dark matter, which acts like a cosmic scaffold, pulling them into dense regions. Over time, these regions grow as more galaxies are drawn in, colliding and merging to form the massive clusters we observe today. These collisions are not gentle encounters. When galaxies collide, their stars rarely collide directly due to the vast distances between them. Instead, their gas clouds interact, compressing and heating up, triggering bursts of star formation. Meanwhile, the dark matter halos surrounding the galaxies pass through one another, creating a gravitational tug of war that reshapes the entire cluster. The result is a dynamic, ever-changing structure where galaxies are constantly moving and interacting, influenced by the gravitational dance of dark matter. Galaxy clusters are not just collections of galaxies, they are also filled with hot gas, known as the intracluster medium, which emits X-rays as it is heated by the collisions. This gas, along with the dark matter, plays a crucial role in shaping the cluster's structure and evolution. The immense gravitational pull of the cluster can even bend light from distant objects, a phenomenon known as gravitational lensing, which allows astronomers to map the distribution of dark matter within the cluster. The formation of galaxy clusters is a key piece of the puzzle in understanding the large-scale structure of the universe. These clusters are the nodes in the cosmic web, the vast network of filaments and voids that make up the universe's architecture. By studying how they form and evolve, we gain insights into the role of dark matter, the nature of gravity, and the history of the universe itself. As we continue to explore these cosmic giants, we uncover more about the forces that have shaped the universe from its earliest moments to the present day. Now turning to the formation of the cosmic web, we explore the intricate network of filaments and voids that define the universe's large-scale structure. This vast cosmic tapestry, stretching across billions of light-years, is the result of countless collisions and gravitational interactions over the history of the universe. Picture it as a colossal spiderweb with galaxies and galaxy clusters strung along its threads, separated by immense, empty voids. At the heart of this structure lies dark matter, the invisible scaffolding that shapes the cosmic web. Dark matter's gravitational pull draws ordinary matter, gas, dust, and galaxies into dense filaments, while leaving behind vast, empty regions. These filaments intersect at nodes where galaxy clusters form, creating a network that connects the universe on the largest scales. Dark energy, on the other hand, plays a different role. It drives the accelerated expansion of the universe, stretching the cosmic web over time and influencing how galaxies move within it. The formation of the cosmic web began in the early universe shortly after the Big Bang. Tiny fluctuations in the density of matter, amplified by gravity, grew into the seeds of the web's structure. As the universe expanded, these seeds evolved into the filaments and voids we see today. Collisions between gas clouds and the gravitational pull of dark matter caused matter to clump together, forming the first galaxies and galaxy clusters along the filaments. Over billions of years, this process continued, weaving the intricate pattern of the cosmic web. The cosmic web is not static, it is constantly evolving. Galaxies and clusters move along the filaments, pulled by the gravitational forces of dark matter. As they collide and merge, they reshape the web, creating new connections and altering its structure. This dynamic interplay between dark matter, dark energy, and ordinary matter shapes the distribution of galaxies and influences the universe's evolution. Studying the cosmic web provides crucial insights into the nature of dark matter and dark energy, as well as the history of the universe. By mapping the distribution of galaxies and observing how light bends around massive structures, astronomers can trace the web's filaments and measure the effects of dark matter and dark energy. These observations help us understand how the universe grew from its initial, nearly uniform state into the complex, interconnected structure we see today. The cosmic web is a testament to the power of gravity and the unseen forces that shape the universe. It connects galaxies across vast distances, revealing the underlying architecture of the cosmos. As we continue to explore this immense network, we uncover more about the forces that have shaped the universe from its earliest moments to the present day, bringing us closer to understanding the grand design of the cosmos. Now turning to the formation of the first planets, we delve into the chaotic yet awe-inspiring process that gave rise to the worlds we see today. Picture a young star surrounded by a swirling disk of gas and dust, a protoplanetary disk. Within this disk, tiny particles of dust began to collide and stick together, forming the building blocks of planets. Over time, these collisions grew more frequent and intense as gravity pulled the particles into larger and larger clumps. As these clumps grew, they began to attract even more material, creating planetesimals, rocky bodies ranging from a few meters to several kilometers in size. These planetesimals continued to collide and merge, driven by the relentless pull of gravity. Some grew into protoplanets, the precursors to the planets we know today. This process, known as accretion, was not a gentle one. It was marked by violent collisions, with some bodies shattering upon impact, while others merged to form even larger objects. The diversity of planets we observe today, rocky worlds like Earth, gas giants like Jupiter, and icy bodies like Neptune, can be traced back to these early collisions. The composition of a planet depended on its location within the protoplanetary disk. Closer to the star, where temperatures were higher, only metals and silicates could solidify, leading to the formation of rocky planets. Farther out, where it was cooler, ices and gases could condense, allowing gas giants and icy worlds to form. These collisions also played a crucial role in shaping the orbits of planets. As protoplanets interacted with each other and with the remaining material in the disk, their paths were altered, sometimes leading to dramatic shifts in their orbits. Some planets were flung out of their systems entirely, becoming rogue planets drifting through space. Others settled into stable orbits, forming the orderly systems we see today. The formation of the first planets was not just a series of random events. It was a delicate dance of gravity, collisions, and accretion. Each collision left its mark, shaping the size, composition, and orbit of the resulting planets. This process laid the foundation for the incredible diversity of planetary systems we observe across the universe. from our own solar system to the countless exoplanets orbiting distant stars. As we reflect on the formation of the first planets, we gain a deeper appreciation for the dynamic and ever-changing nature of the cosmos. These early collisions not only shaped the worlds we see today, but also set the stage for the emergence of life and the ongoing evolution of the universe. With this understanding, we move closer to unraveling the mysteries of our cosmic origins and the intricate processes that continue to shape the universe. Now turning to the conclusion of our journey through the cosmos, we reflect on the 25 massive cosmic collisions that have shaped the universe as we know it. From the explosive birth of the universe in the Big Bang to the formation of galaxies, planets, and even the very elements that make up our world, these collisions have been the driving force behind the evolution of the cosmos. Each event, whether it was the collision that formed our moon or the asteroid impact that wiped out the dinosaurs, has left an indelible mark on the fabric of space and time. These cosmic collisions remind us that the universe is a dynamic and ever-changing place. They have not only shaped the physical structures we see today, but have also played a crucial role in the emergence of life and the ongoing evolution of the cosmos. From the smallest particles to the largest galaxies, every corner of the universe bears the scars and stories of these monumental events. As we look to the future, we know that cosmic collisions will continue to shape the universe. The impending collision between the Milky Way and Andromeda galaxies, the constant bombardment of asteroids and comets, and the ongoing formation of stars and planets all remind us that the universe is far from static. These events are not just remnants of the past, they are the building blocks of the future. We hope this exploration has deepened your understanding of the universe and the incredible forces that have shaped it. What are your thoughts on these cosmic collisions? Which event fascinated you the most? Share your thoughts in the comments below, and don't forget to subscribe for more space mysteries. Together, let's continue to unravel the wonders of the cosmos and uncover the secrets that lie beyond the stars.